A normal radio uses AM and FM modulation techniques and acts as a receiver always. But when it comes to Bluetooth radio, it uses GPSK, Gaussian phase shift keying, and acts as both receiver and transmitter, but not both at the same time. The frequency band of Bluetooth is from 2400 MHz to 2483.5 MHz. This frequency band is divided into 79 frequency channels. As shown in this table, you can put K value from 0 to 78 to get all 79 channels. 32 among this 79 are used during enquiry and enquiry scan. Apart from the frequency channels, we have two guard bands, 2 MHz lower guard band and 3.5 MHz upper guard band. Remember this 32, we will be using this number often in the coming slides. We will focus mainly on the usage of these channels during enquiry and enquiry scan. Just think that these are 79 frequency channels in the Bluetooth frequency band. This animation depicts the communication between two devices, device 1 and device 2, when they are already connected. As you can see here, device 1 is transmitter and 2 is receiver. Here data is sent from device 1 to device 2. The roles of two devices are switched, and then device 1 acts as receiver and device 2 as transmitter. And after this, device 1 will switch its frequency to another channel, and again the same thing happens. Device 1 as transmitter, 2 as receiver, and sends the data, and device 2 will send back the acknowledgement. So device 1 is hopping in the sequence, and device 2 is also hopping in the same sequence in which device 1 is hopping. So when device 1 comes to the third hop frequency, again it sends the data and receives back. So to communicate in this way, one device needs to know the other device hopping sequence. After a successful enquiry scan between two devices, one device will get to know the FHS of the other through FHS packet. This packet carries the information of hop sequence. We will see the graph in the coming slides. This is the format of Bluetooth packets which are used in communication between BT transmitter and receiver. Any data that goes out of Bluetooth device will be in any one of the three formats. So basically a packet contains three parts: access code, header and payload. We can use in three ways this packet. We can use it with only shortened access code, and otherwise we can use access code and packet header, and the next one is we can use all the three components of the packet. For inquiry, we use shortened access code. So let's get into what is access code. This is the format of access code. This again has three parts: preamble, sync word and trailer. Why we use trailer is basically to say this is the end of the access code. Trailer of access code is used when there is header in the BT packet. But when we are sending only access code, this trailer is not required. So the last 4 bits of access code are removed to make it 68-bit shortened access code, which we generally call it as a ID packet. Now we will see what is preamble and sync word in access code. Preamble depends on first bit of sync word. If the first bit is 1, the preamble is 1010, or else it is 0101. These are the 4 steps for the construction of sync word. Before looking into this, we should see the format of Bluetooth address. Generally, Bluetooth address consists of 3 parts: LAP, UAP, NAP. LAP is organizationally unique identifier, so each organization will have a unique LAP. UAP and NAP are assigned by the organization. Now let's get into the construction of sync word. LAP of the Bluetooth address is used in this process. LAP is basically a 24-bit address to which we add a trailer of 6 bits to get 30-bit data. These 6 bits are based on last bit of LAP. P34 to P63 is the pseudo-random noise. We XOR 30-bit data with PN sequence and generate the data, which has to be encoded. Then we add parity bits for X0 to X29 to generate the code word, 64-bit code word. This code word is XORed with 64-bit PN overlay sequence to generate the sync word. This is the RxTX graph of Bluetooth radio. Here we have two slots, Rx slot and Tx slot. In Tx slot, the transmitter is at one frequency f of k and sends a packet for 68 microseconds. Then it will wait until 312.5 microseconds, switches to next frequency and again sends another packet. Now the device will switch its role as receiver, which is Rx slot now. Again it enters f of k to receive the response for the packet which was sent before, then hops to f of k plus 1. In the first graph, master and slave are at same frequency. So slave is sending the response for the first ID packet sent by master. Once the ID packet is received, the slave starts a timer of 625 microseconds and sends the response, which is FHS packet. FHS packet contains details about the hop frequency of slave. In the second graph, slave responded to the second ID packet, and here also same timings are followed, and there is a EIR bit, extended inquiry response bit, in FHS packet. If this bit is set, then the master waits for the extended inquiry response packet. Here master will not hop to the next frequency and stays in the same frequency in which it has received the FHS packet. This extended inquiry response packet contains the class of device and other details of the slave device. There is a sequence diagram between master and slave when inquiry and inquiry scan is being performed. So master has two states, standby state and inquiry state. Slave is also having two states, standby state and inquiry scan state. So standby state is something we can say the device is idle, and in inquiry state, uh, the device will send the ID packets continuously. And on the slave side, if the slave is in standby state and if the master is in inquiry state, in that case the ID packet sent will be lost. As you can see here, the first ID packet received, which is in at that time the slave is in standby state, so this packet is lost. But when the second ID packet is received, the slave is in inquiry scan state, so it waited for one slot, which is 625 microseconds, and sent back the FHS packet. So this one we have seen in a graph in the previous slide. Now let's look into the timeline graph of inquiry and inquiry scan. Here we have two values of time, T inquiry and T window inquiry. T inquiry is the time taken to complete inquiry and standby state. We can take it as one inquiry cycle. T window inquiry is the time in which ID packets are sent out of the device. T window inquiry can be expanded as 256 times A and 256 times B, and again 256 times A, 256 times B, and this continues until T window time. Here A means train A frequencies and B means train B frequencies. 1A will look like this. First, device will send ID packets in two frequencies and then it waits for the response in same two frequencies. As you can see here, device is now sending the ID packets in F13, F14 and waiting for response in again F13, F14, and this one is continuing for all the frequencies. Totally has 32 sectors, each of 312.5 microseconds. Here one slot is 625 microseconds, so totally we have 16 slots. In one slot, device is transmitting ID packets. In the next slot, device is waiting for response. So in this one train, 16 frequencies are used. Now inquiry scan. Again, inquiry scan is also having two values of time, T window inquiry scan and T inquiry scan. T inquiry scan is the time taken to complete inquiry scan and standby state. We can take it as one inquiry scan cycle. T window inquiry scan is the time taken in which the device will be listening for the ID packets. Now let's see how all the 32 frequencies are used during inquiry and inquiry scan. This is basically the usage of train A frequencies during inquiry. Here each sector is 312.5 microseconds. So totally we have 32 sectors. So total time taken to complete one train of frequencies is 10 milliseconds. This repeats 256 times. So total time taken to complete 256 times is 256 into 10. So total is 2.56 seconds. Here it switches frequency every 312.5 microseconds. The remaining frequencies are covered by train B. Here also we have same timings. You can just observe the train of frequencies, how they are getting used. Now we will look into enquiry scan. Here device will listen in all 32 frequencies, but with an enquiry scan interval of 1.28 seconds. So these are the default values which I have taken all the timings. As default value of enquiry scan window is 11.25 milliseconds, the device will be listening to the ID packets of each frequency for 11.25 microseconds. We can see that the frequency switching is happening every 1.28 seconds. Just observe the way in which enquiry scan is getting performed. This is how enquiry and enquiry scan happens in real time. The device which performs enquiry is master and the device that performs enquiry scan is slave. The speed of rotation is not correct here. The rotations in the master will be very much faster than the slave as it happens in milliseconds. When both the devices switch to same frequency, then that is the first point of communication between two devices, followed by sharing of FHS packet.